thermoplated composite is the first point of contact for customers who are interested in lightweight solutions. In addition to our technical lab, the production and process development is also located here. On the one hand, Engel offers equipment for the processing of thermoset composite parts, like for example HBR-TEM, but we can clearly see the trend toward to the thermoplastic composite material. The organomelt technology, which means the thermoforming and back injection of organosheets or cross plies, is therefore a very important technology for us. This technology has been expanded in the recent years by the tape placement and the consolidation technology. Today, I would like to give you a closer look to the process of thermoplastic tape to the finished part. The main focus will be on the tape stacking and the consolidation process. Therefore, I'm pleased to mention that we won the Czech Award for this process category. Today, I would like to show you the way from the idea to the finished product by using a demonstrator part. On the left side, you can see the product levels like simulation, tape stacking, consolidation, and the formed and back molded part with injection molding. At the right side, you can see a possible layout to produce this part. With this layout, it is possible to produce this part in about 70 seconds. And this is the reason why we think that thermoplastic composites will become very popular in future. Complex parts can be produced very quickly, and additional functions can be integrated by injection molding. Now I want to go deeper in the process, starting with the tape stacking unit. The automated tape stacking technology of Engel follows the pick and place approach. With our E6 robots, the tape segment can be built up to a tailored and net-shaped tape stack. To achieve high laying rates and high laying precision, the system is supported by an optical measurement device. This allows a correction of the position and of the angle orientation to produce high quality semi-finished parts. This layout shown here is able to produce parts with a maximum dimension of 460 to 360 millimeters and is located at the LIT factory in Linz. Current investigations focus on a proof of concept with a maximum stack dimension of 1.1 meter to 600 millimeter. To get a better understanding how the system works, I would like to go a little more deeper in a little more in detail. The storages are located around the robots and loaded with pre-cut tape segments. Besides storing, the main task is the separation of the tape and supply of one single tape at the pickup table. For the movement between the different stations at the tape stacking process, 2 fast E6 robots are used. These robots are equipped with special end-of-arm toolings. Yes. These end-of-arm toolings are equipped with a lot of technique like pneumatic cylinders, sensors, suction cups to pick up the tapes, and also welding stamps to spot weld the tapes. Furthermore, an illumination foil on the bottom is installed. Currently, we are developing a spool magazine that is able to provide tapes with a specific length needed directly from the spool. With the modular end-of-arm tool, only the backlight mounting plate is product specific. This is this one. The suction cups and the welding rods can be moved in the whole grid of the perforated blade. This means that only the backlight mounting plate has to change for a new project. For the tape detection, a high contrast between the tape and the backlight is necessary for the optical measurement system. Therefore, it's very important that the backlight film has only openings for the suction cups and welding rods, and that these openings are located or not located at the edges of the tapes. With a single tape, this is not the challenge, but if you have to take several tapes, you have to be careful here. And to place the tapes most accurately, the system has to know the exact position of the tape at the end of arm tool. Therefore, the measuring device consists of a table with an anti-reflective glass plate and a high-resolution camera below this glass plate. The robot, and in the process, the robot pushes the tape against this glass plate to completely straighten the tape. And at the same time, the vision system takes a picture of the tape at the end of arm tool. You can see such a picture on the top right. By shape shirts, edge and corner point detection, the exact position of the current tape at the end of arm tool can be determined. Now the system knows the current position of the tape at the end of arm tool and also the position of the previously placed tapes which are already on the stacking table. This allows to build up a layup with almost no gap or no overlap. At the test setup, a placing accuracy of plus minus 0.2 millimeters could be achieved. After the measuring step, the tapes are placed on the stacking table. The first layer can fixed by vacuum. All followed layers are welded to the layer below by spot welding. This sequence is repeated until the complete stack has been laid down by the system. The removal of the finished part can be realized by a conveyor belt. During the processing, a thin layer of thermoplastic material can be built up at the tip of the welding stamp over time. The degree of accumulation depends strongly on the type of polymer. This layer can have a negative effect on the spot welding process. The three pictures at the top shows the tip after 10, 50 and 100 welding operations. This issue has been solved by implementing of a periodic and automatic pyrolysis process. Therefore, the welding units are heated up after a certain number of welding operations to a temperature above 600 degrees Celsius. The diagram left shows the pyrolysis cycle, and you can see that after 30 seconds, the working temperature has reached again, and so we can start a new welding. The picture on the bottom right shows the welding. Sorry, that's going. Oh, yeah. The picture on the top, on the bottom right, shows the picture. Shows the welding unit after the pyrolysis process. It's completely free of polymer residuals. In the consolidation unit, all layers are melted and cooled down to produce a tape blank. The process starts in the loading and unloading station. First, the thin mold plates were opened and the tape stack can be inserted. If the tape stack has very wall thickness, the different wall thickness are also included into the mold. After the tape stack has been inserted into the mold is closed. By using 3 sets of molds, there is always one mold in the heating press and one in the cooling station. This allows a very fast process, and a tape stack with a thickness of 3 millimeters can be produced in a time less than 1 minute. The graph on the right shows the temperature curve in black and the pressure curve in red over the cycle time. In the heating station, the tape stack is heated up under low pressure. When a target temperature has reached, the stack is transported to the cooling station and cooled down under higher pressure. During the cooling process, the energy balance of the process can be increased significantly. As warmer the stack can be removed, as better is the energy balance. Because of the remaining heat in the molds, and this heat can heat up the stack during the transport. You can see this shown here. On the left side, you can see such a layer produced at the tape stacking unit. In this case, it consists of an organo sheet as glass fiber, and 6 tapes with carbon fiber. The picture on the right shows the consolidated part, which is ready for further processing steps. You can also see the different wall thickness, and it's perfectly consolidated. In the next step, the consolidated tape blank must be heated above the melting temperature. Engel uses infrared heating technology. Depending on the application, 2 different kinds of ovens can be used. For very thin semi-finished products, a vertical oven